Hello everyone, welcome to Electronically Connected. We're going to be talking about the logic gates using CMOS, that is the PMOS and the NMOS transistors. We will also be discussing the truth tables and the symbolic representation of our logic gates. We will be covering the inverter, the universal gates, the AND, NOR and the exclusive gates. So let's get started. So the very first gate that we will be covering is my NOT gate, also called as the inverter. The NOT gate is symbolically represented like this, where one side we have the input A and we get the output Y. Let's understand the truth table. If we have our input A and my output Y, if the input is 1, the output we get is 0. That means it's inverted. Similarly, if the input is 0, then the output we get is 1. Let's understand the diagram of the NOT gate using a transistor, which we have also covered in the previous video. Here we have the input A and the output Y. The PMOS is connected to VDD and the NMOS is connected to ground. So this is what a NOT gate looks like using the transistors and the symbolic representation and the truth table. Moving forward to the next gate, we're going to be covering the universal gates first. This is the NAND gate. The NAND gate is represented as Y is equal to A dot B bar, and symbolically it's represented as AB as the inputs and Y as a output. The bubble is the bar that we see on the top of A dot B. Let's understand the truth table. If the input is A and B and Y as the output, because we have two inputs, there are 4 types of combinations that we are going to see as my inputs. Let's go through all the 4 combinations. That is 0, 0, 0, 1, 1, 0 and 1, 1. So when my input is 1, 1, then only my output is 0. Rest all the other times my output is 1. Let's understand the diagram of NAND gate using a transistor. So here we have the transistor diagram of the NAND gate with inputs A and B on the PMOS side, and it's connected to the same inputs at A, and it's the same input actually connected like this. So now we have the VDD, the ground and the output Y. Let's test if the output that we get is according to a truth table. So let me understand this condition. If A is equal to 1 and B is equal to 0. So if A is equal to 1, B is equal to 0, A is equal to 1 and B is equal to 0. When we see from the NMOS side, as this is 0 and 1, that means there is no direct path between the output and the ground, as the NMOS is off in this condition and it's on, but it is not directly connected. But in the PMOS side, we can see that A is 1 and hence it's not connected. B is 0, hence this PMOS is working and there's a direct path connected between the VDD and Y. Therefore, we get as output as 1 and hence this is working. Moving forward, let's understand the next gate that we have. Here we have the NOR gate. It is another universal gate. The NOR gate is represented as A plus B bar. Let's see how it looks symbolically. So we have the inputs A and B and Y as the output. The bubble again represents the bar that we see on the top. Let's understand the truth table. Again, we have 2 inputs. Hence, we'll have 4 combinations in my input side. So 0, 0, 0, 1, 1, 0, 1, 1. And the output is 1 only in the case when both my inputs are 0. Let's understand now the transistor diagram of the NOR gate. This is the transistor diagram of the NOR gate, where we have our inputs A, B in the PMOS side and A and B on the NMOS side with Y as my output. Let's check one of the workings using one of the inputs. Let's understand this input. So we have A as 0, B as 1, A as 0 and B as 1. So we know that the PMOS is turned on when the input is 0. So we have a direct path over here. But however, the PMOS is turned off in this condition when the B is 1. hence it's open. The switch is open. That means there is no direct path connection between the VDD and Y. Now looking to the NMOS side, we see that the NMOS is turned on when the input is 1, and hence this side of my input is turned on and there's a direct path, and the NMOS is off. So there's a direct path between the ground and the output, and hence the output is 0. Thus we have verified the working of the NOR gate with this input 0 and 1. Now how do we remember the diagrams of our NOR gate or NAND gate? Let's see. So we saw that the NAND gate is A dot B bar and the NAND gate was A plus B bar. If we recall that, we will remember that the NAND gate had A and B in parallel in my PMOS section. So we had our A and B in parallel, but in NOR gate we had the A and the B in series. This was the parallel connection of A and B and the series connection. So let's make a note over here. In situations where we have A dot B, the PMOS is the inputs A and B are connected in parallel in the PMOS, and in the cases where we have A plus B, the inputs A and B will be connected in series in the PMOS. So we just have to remember one of the cases. So if there's a dot, that means it's going to be parallel, and if it's a plus, it's going to be in series. And all of this applies only to the PMOS, and the opposite convention happens in the NMOS, where the A and B gets in parallel in the NMOS for a NOR gate, and A and B gets into series in the NAND gate. Moving forward to the next gate, that is the OR gate. OR gate is written as Y is equal to A plus B without the bar, because it's an OR gate. Symbolically, it is similar to a NOR gate minus the bubble. So we have A, B and the output Y. Let's see the truth table of our OR gate. You must have guessed that because there is no bubble on the OR gate in compared to the NOR gate, the output is going to be just the opposite of my NOR gate. So we're going to have 0, 1, 1, 1 for my OR gate. Let's understand the diagram of our OR gate using the transistor. The OR gate diagram looks very much similar as a NOR gate, except that we have an extra CMOS in the end, because we need to negate the bar that was present in the NOR gate. So the first part of the OR gate is similar to a NOR gate plus a CMOS, that is an inverter, to cancel out the bar according to the De Morgan's law. So we have again A, B, A, B. Let's test it out for one of the inputs. If my input is 1, 0, 1, 0. So again, there is no direct path from the VDD to my output. There is a direct path just from the A side. So we have a direct path over here. That means we have 0 at this end. Now the 0 is the input to the CMOS, and hence we know from the CMOS working, it inverts the input and we get the output as Y. And we can verify the working of a OR gate. Moving forward to the next gate, we have the AND gate. The AND gate works in a negated manner of the NAND gate. So we have Y is equal to A dot B without the bar. Symbolically, it is represented same as the NAND gate minus the bubble. Let's understand the truth table of AND gate. We have two inputs, so 4 combinations, 0, 0, 0, 1, 1, 0 and 1, 1. And the AND gate is 0, 0, 0, 1. It's just the opposite outputs of the NAND gate. Let's understand the diagram of an AND gate using transistors. So here we have the diagram of the AND gate, which is again a combination of my NAND gate plus my CMOS to negate the bar on the output. So we have A, B, A and B. Let's check one of the inputs to verify the diagram. If our input is 1, 0, 1 and 0, so there's no direct path from the ground to the output, and hence all the NMOS is of no use. In the PMOS side, we can see 1 is the input, so hence this is turned off. Only the B input is turned on, hence we have direct path from the VDD to the output, which is 1. And again, because it's a CMOS, it's going to negate my 1 and we get a 0, and hence we verify the input combination of the AND gate. Moving forward to our next gate, we have the XNOR gate. It's y is equal to a bar b bar plus ab, also written as a plus b. So let's see the diagram. This is a symbolic representation of an XNOR. So we have a, b and y. Let's understand the truth table. Again, 2 inputs, 4 combinations. So 0, 0, 0, 1, 1, 0 and 1, 1. So we have 1, 0, 0, 1. Let's understand the diagram for the XNOR using transistors. So here we have the inputs as A, B, A bar, B bar, A, B bar, A bar and B. Let's verify the working of my XNOR gate using one of the inputs. So let's take this for example 1, 0. So we have 1, 0. The 1 becomes a 0 and this becomes a 1. Then we have 1, 1, 0 and 0. So the PMOS is turned on when it's 0 and off when it's 1. So we have transistor turns off, it turns off. So there is no direct path between the VDD and the Y. Then for the NMOS, it turns on when it's 1. So we have a direct path from the ground to the output, and hence my output is 0. And hence it's verified. Moving forward to the next gate, we have the XOR gate. Symbolically, the XOR gate is A and B, my Y output, where Y is written as A dot B. If we expand this, it says AB plus A. This is my XOR gate. Let's understand the truth table of my XOR gate. We have 2 inputs, so 4 combinations again, 0, 0, 0, 1, 1, 0, 1, 1. It's 0, 1, 1, 0. Let's understand the working of the XOR gate with the help of a transistor. So here we have my 2 input XOR gate with A, B bar inputs and A bar P, my output Y. Let's test the working of my XOR gate with one of the input combinations. So let's take 0 and 1. So we have 0, 1 becomes 0, this becomes 1 and 1, so 0, 1, this is 1 and 0. So we don't have any direct path between the ground and the PMOS so we don't have any direct path between the ground and the output, because one of the NMOS is turned off and this is turned on, this is off, so there's no direct path. Moving on to the PMOS, we see a direct path between the VDD and the output, and hence you can see the output is 1 and the working of my XOR is verified. Thank you for watching. Please like, share and subscribe to my channel. See you next time. Till then, happy learning.